We've taken a look at two of the chapters for this coming week in the Brookshire text, so let's take a look at the final one. So the third major topic for this evening, computer logic. Fundamentally, the basic building block of hardware is the switch. When you strip everything else away, what computer hardware really is a switch. Now, you know it's not exactly like an on-off switch on the wall, but in another sense it is. It's certainly not as big as an on-off switch on the wall, and it's certainly not turned on manually, but fundamentally everything inside the computer, hardware-wise, is a switch. I want to give you some insight into where this came from that, although it's a little tiny bit of this in chapter 0, it's not actually in the chapter where it talks about this, which I think would be helpful. In the third unit of this course, we're going to take a look at a little bit of the historic development of information technology. And this is going to be one of the persons that we're going to mention, and that's George Boole. George Boole was an English mathematician, logician, scientist, theologian, sort of like a genius, a Renaissance person. He did a lot of things. In the mid-19th century, he wrote a book. It was called An Investigation to the Laws of Thought. From that, he created something that today we call Boolean algebra. He didn't call it that. The Boolean obviously comes from his name, but people name this in his honor. Boolean algebra is the foundation for computer hardware. Computer hardware works because of George Boole's insight and investigation. All right, so what's up with Boolean algebra? Well, first of all, algebra, all the term means is structure. It scares people because they first learn one kind of algebra, typically in early secondary school, right? There's one kind of algebra, and that's kind of scary to folks. But algebra merely studies the structure of something, okay? Now, in any algebra, we separate our structural elements into a couple basic categories. There are operands. That's like the variables here. Y, M, X, B. Those are the operands. And then we have another category, the operators. In this case, that's addition. The equal sign for us is that assignment operator. Good. Standard algebra, the kind you learned in secondary school. The operands then are, do I have this? The operands are the letters. And this is what always throws folks, right? You know, it's 3 plus 7. I could do that. 3 plus y. What? The operands are letters, and they usually stand for numbers. And that's because standard algebra studies the structure of arithmetic. It's an actual way to abstract or simplify arithmetic. The operators then are the standard mathematical operators: add, subtract, multiply, divide, assign, and other kinds of things. Boolean algebra will be similar. It will study a structure. It will have operands and operators, but the specifics will be different. Just a darn minute. Yesterday you said x equals 2. See how confusing algebra is? Right? I mean, that x thing just varies all the time. Okay, thank you. So what about Boolean algebra? Now again, the reason we're looking at Boolean algebra, This is the foundation for hardware. Currently, hardware works, is constructed and designed using concept of Boolean algebra. Well, there are operands, there are variables, and they could be represented by letters, but the thing that makes Boolean algebra both interesting and easier is they don't represent values. They represent numbers, at least. They represent these two concepts, true, false. Interestingly, any Boolean algebra equation, you could guess at the answer, and half the time you'd be right. Because the only answer to a Boolean equation is true or false. Can't do that with standard algebra, can you? Right? I mean, there's a lot of different numbers. Too many to guess from. The operators are strange. It's not add, subtract, multiply, divide. The operators are things like not, and, or. At least George Boole had the sense to choose terms that in English match the function of these operators, and we'll see that. Okay. All right. Oh, we need to talk about Aristotle. I'm not going to do that. The other thing I want to share with you, though, is something I'm going to share with you when we look at all the historic personages involved in the development of information technology, and also just technology, including computers. And that's their specific worldview. Now, last time we talked about this concept of a worldview just a little bit, and we noted that in this program, in the MSIT program, there's one specific course that's going to focus on that a lot. That's the 10 class, Ethics and Vocational Computing. But as a matter of fact, we're going to be talking about worldviews or how people philosophically approach things a lot also. George Boole, and this is just a quote from his book. I gave you the title of that 1854 book. George Boole wrote that my worldview really springs from, quote, an intellectual allegiance to the Father of lights. Now, you don't have to remember that phrase. I just want to connect the dots for you. Father of lights, that doesn't mean anything to us today. This was, however, a pretty common phrase in the 19th century. It's actually a quote and an allusion to a biblical book, the New Testament book of James. James, who is the brother of Jesus, wrote in his letter, "Every good and perfect gift is from above, coming down from the Father of heavenly lights, who does not change like shifting shadows." George Boole had a decidedly Christian worldview perspective. And the reason I bring that out is, according to Boole in his book and in his writings, that gave him great insight into developing some of the things that he did, including Boolean algebra. The moral of the story is, technology, inventions, ideas, they don't just suddenly spring forth in a vacuum. Somebody doesn't just, oh, I think I'll do this. It's all connected. Their ideas, their perspective, their philosophy, their worldview all help shape how they think about problems, how they think about solving problems. We'll say more. Now, back to switches. Computer hardware is a switch. A switch fundamentally has to do two things. A switch has to, first of all, represent stuff. A computer is just, a CPU is just a bunch of switches. How could possibly a bunch of switches represent anything? I think you know the answer. Now you're saying, wait, binary form, what's that have to do with a switch? You probably know. What's binary form have to do with a switch?
Zeros and ones.
Yes.
And electricity, that's
Yep. Yep, exactly. Zeros and ones are offs and ons, right? Today, if you pick up any piece of consumer electronic, the power button does not say on or off. Instead, almost universally, the power button says 0, 1. The universal on-off, right? That's a 1 and a 0. 0's off, 1's on. So, exactly. So, sorry. So, when we had 0, 1, 0, 0, truly what's happening is off, on, off, 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 on, off. Just a lot easier to say 0 and 1, right? Nobody wants to say off, on all the time. What this is, let me connect the dots one more way. What we're really talking about here is abstraction. Technically, the hardware is a bunch of on-off switches. But we simplify that. We think about it in terms of zeros and ones. And remember, this abstraction works by agreement. Why is 0, 1, 0, 0, 0, 0, 0, 1? Why is that a capital A? Because the ASCII committee said so. Because a group of individuals got together 40 years ago and said, here's an A. Now, if you don't like it, that's fine, but then you just can't play with the rest of the world, right? Everybody says that is an A. Why? By agreement. Okay, so first of all, switches have to represent stuff. Letters, numbers, sounds, instructions. Secondly, switches need to process stuff. Computers need to add, subtract, multiply, divide, compare values. That's processing. Switches are all it's got. So this gets even worse. How does an on-off switch, or even a bunch of on-off switches, how does that allow a computer to add, for example? All right, here's the answer. The answer is Gates. This is not William Gates III, Bill Gates, the founder, former CEO of Microsoft Corporation. Okay. In IT, a gate is a combination of switches which perform a Boolean function. A gate is a combination of switches which perform a Boolean function. Chapter 1, Brookshire starts actually on the second page of Chapter 1 talking about gates and immediately wants to talk about something else known as flip-flops. You could ignore flip-flops. But a gate is a hardware construction. It's a piece of hardware. It's built out of switches, and these combination of switches perform a Boolean function. So let's look at that. Brookshire talks about more, but I just want to introduce in a slightly different way 3 basic gates. The first gate is called a NOT gate. Well, if it's not a gate, what is it? No, it's just called a NOT gate. This is its symbol, this triangle with a little dot on the end. You don't have to remember that. When computer scientists draw circuitry, they'll draw things like that. What I want us to know as information technologists is, so what does this gate do? And then ultimately, how does that help us process stuff? Well, first of all, gates are really simple things. In the world of computer hardware, there's only 2 entities, right? 0, 1. That's it. This is the simplest possible gate. It takes a single input, it takes a single binary value, and then it returns another single binary value as output. Now, to understand how it works, sometimes people draw what are called truth tables. truth table will just list all the possible combinations. In this case, because there's only one input, there's only two possible values for the input, right? 0 or 1. You can probably tell by the name of the gate what happens. So yes, what is not 0? A 1. A NOT gate gives us the opposite. So how do you read this thing? Well, read it a record or a row at a time. If the input happened to be a 0, then the output of the NOT gate be the 1. If the input happened to be a 1, then the output would be a 0. Now, this one is simplistic, I know, but I want to illustrate the point. For more complex gates, you could either memorize the truth table, or you could stop and think, what does the word mean? In English, the word not means the opposite. If it's not a 0, it's a 1. Think about how you use the word in everyday speech. This is Jesus talking to Nicodemus, and recorded in John 3. God so loved the world, he gave his one-of-a-kind Son, that whoever believes in him shall not perish. By not, Jesus meant the opposite. And then he went on to explain what that was. Not perishing means eternal life. So the NOT gate, like all the other gates, even if you can't remember the truth table, if you think about the word and its meaning in English, that will likely help you figure out what's happening here. The second gate, a little more complex than the NOT gate. This is the OR gate. You don't have to remember its symbol. I'd never ask. This thing looks like the Starfleet symbol turned on its side. That's an OR gate. Now, what makes it a little more difficult than the NOT gate is, notice there are two inputs producing a single output. That means the truth table will also be bigger because there are 4 possible combinations. What the OR gate does is it's going to look at both of those inputs, and depending upon the values of those two inputs, it will make a determination as to the output. Are you ready? So again, truth table, inputs on the left side, outputs on the right side. This time it's a little more complex, though, because there are 4 combinations. Both of the inputs might be a 0. The first might be a 0 while the second's a 1. The first might be a 1 while the second's a 0. Both of the inputs might be a 1. Now in this case, to try to put the OR concept with it, it's easier to think in terms of true and false rather than 1 and 0. That's how George Boole thought. 1s are trues and 0s are falses. Let me give you the answer, and then let's see where that's coming from. Notice that the output in every case is a 1 except for the first, when both inputs are a 0. This is saying 0 or 0, answer 0. In every other case, though, the answer is a 1. Why? It's how we use the term or in everyday speech. Imagine that these are 2 clauses. You're going to say, I'm going to do something if or When we say or, we mean either one or the other or both are true, then I'll do it, right? Yeah. So again, when you see an OR gate, think either. For example, when Jesus talking to the crowds, as recorded in Matthew 10, he said, anyone who loves his father or mother more than me is not worthy of me. Of course he meant you either love one or the other, or of course both. Right? Yeah. That's how we use or in everyday speech. So it might be helpful again to think in terms of trues and falses, and then true or false. Well, it's an or, so the answer is true. final gate is the AND gate. Now, I shouldn't say final one we'll care about, is the AND gate. A different symbol, looks a little different than the OR gate, you don't have to remember it. Like the OR gate, it has two inputs with a single output. What that means is the truth table will have a similar structure. There are 4 combinations that work here. And there's the same 4 combinations of inputs that could be supplied to an AND gate as there was an OR gate. It might be both are 0. It might be the first is 0 while the second's a 1. The opposite of that. And finally, both are 1. The truth table is different because the outputs are different. If they were the same, it'd be the same gate. Let me show you the outputs and then let's figure out where they came from. You'll notice in this case that the only time the output is 1 or true is when both of the inputs are true. Imagine you're looking at a true-false question on an exam, and you know those tricky ones, right? There's that clause in there. There's an and in there. And you look at it and say, well, okay, one part of it's false, but the other part is true, so what do I write? False, that's right. That's what this is saying. If you have 2 clauses separated by the word and they're both false, what's the sentence? False. False or true. False and true. Nope, if there's an and, then it's false. The only time that our sentence is true using an and connection is when both of the clauses are true. And that's what that's saying. So again, in everyday speech, the word and means both. So when Jesus talking to his disciples says, I tell you the truth, whoever hears my word and believes him who sent me has eternal life, both of those have to be true. If you just hear the word but don't believe, no. And you can't believe without hearing the word. So both of those conditions have to be true for that statement, that clause to be true. So, not, opposite, or, what did we say for or? Either. Yeah, I was hoping somebody would say either. You could say it either way, right? And finally, and means both. All right, what in the world does this have to do with adding numbers? Glad you asked. Let's add some numbers. Now remember, computers use binary. When we're adding numbers, we use base 2 binary form. Believe it or not, all of binary addition is really formed out of, well, okay, there's actually another case, and one of these is a special case. But really, I mean, there's just 2 values, 0, 1, right? And I've got 4 combinations of it. I bet you can do this even in base 2. 0 plus 0? That's it. 0 plus 1? That's it. 1 plus 0? Here's the tricky one. 1 plus 1? Yeah, 0 carry the 1 or 1, 0. There's no 2. No 2 in base 2, right? It's 1, 0. Now, to make our discussion simpler, I'm going to ignore this last case. It actually comes as a special case, and with adders we have to have a carry in anyway. So, all right. Now, creativity is oftentimes seeing the same thing that everybody else sees, but in a slightly different way. In the 20th century, there was a big breakthrough because somebody looked at this that everybody else had looked at and also saw something else. Does this look familiar? Does this look familiar? There are the rules for base 2 addition. We just talked about one kind of gate, the OR gate. Watch. 0 plus 0, 0. 0 or 0, answer 0. 0 plus 1, 1. 0 or 1, answer 1. 1 plus 0, 1. 1 or 0. And now, this last one is a special case, and we have to do something about it, strictly speaking. But you see the point? The foundation for processing is gates. How computers do addition is based loosely on the OR gate. How do computers add? Which gate forms the foundation for addition? The answer is the OR gate. Exactly. Are computers thinking when they add numbers? No. What are they doing? Just sending bits through gates. And something happens, right? Absolutely. Answer? OR gate. So what we're saying is this. At the lowest level, hardware is really simple. It's just a switch. It's a bunch of switches. But I can use those switches to represent stuff when I talk about these encoding schemes using the concept of abstraction. And I can also get these gates to process things by making that connection to Boolean algebra. Hardware is simple, just a bunch of switches. I don't want to do that. Do I have to do any of this other stuff? I should. Look, there's some funny pictures and stuff. We need to pause, though, because I do want to say a couple things about the upcoming set of assignments, and I want to make sure that there's time to do a lab exercise also. So, should have had this already. I don't. I apologize. Hey, what's happening? Hello? If you haven't done so already, I would encourage you, for those of you on campus, to take a look at one of the course casts. Make sure you can access it. There may come a time when you actually need to be able to see it, and if there's something wrong with your software or hardware and you're unable to access it, then there's just going to be some weeping and wailing and confusing. Confusing? For those of you at a distance, you've obviously watched the course cast, otherwise you wouldn't hear me saying that. Right? There are lots of variables in any IT system. Different computer hardware, different communication networks, different operating systems, different browsers, and other problems too. So if you haven't looked at one of the course casts, and you might haven't felt any need to, and if you never do, that's great. But I want to encourage you to look at one now before you actually need to see it. There may come a time in the future when you want to double check something I said, or like when we were going through the macros, you want to see something again there, and then I'd be able to help you, but at the last second I may not be able to. Okay? All right. Today, when those of you on campus take a look at the Lessons tab, you'll notice there's a new folder. It's Unit 2. Within Unit 2, you'll see several different assignments. 4 for the today, and, well, oh yeah, let's go together. 4 for next time. These are just the instructions for the actual quiz itself. There are 3 major assignments in each of the units, focusing on one of those chapters in Brookshire. Let me just share the questions with you so that you know. Now, up front I said, I'm going to base everything on the 11th edition of Brookshire. It's the version I'm using. If you don't happen to have the 11th edition, the questions might be in a different place. That's why, rather than just saying do question 1, 24AB 26, I started there by giving you some of the words associated with it so you can figure out which one it is. Number one, determine the output for each of the following circuits. What Brookshire has there, and I know you can't see what I'm holding up here, but he has these little circuit diagrams. And they are NOTs, ANDs, ORs, and one other type of gate that Brookshire likes, and that's the XOR, exclusive OR. So what you'll have to do is he'll tell you, okay, assume the upper input's a 1 and the lower input is a 0. What would the output be? Now, I don't want to do that specific circuit, but let's just do a different one. So you can see what's happening. This is supposed to be an OR gate. This is supposed to be a NOT gate. So Brookshire says, well, imagine the upper input's a 1 and the lower input's a 0. So what's the output of that gate? That's correct. Now, how do you get that? First of all, this 1 goes into the NOT gate, becomes a 0. So now the two inputs to the OR gate are 0 or 0. Answer? 0. You got it. So what you're going to do is a similar kind of thing, only there's sometimes more gates, and then there's that new one, this XOR. You don't have to have anything memorized here. You could just look it up, right? There's a truth table for all those gates I showed you, and then Brookshire will show you how the XOR works. So just look it up. You don't have to have it memorized. Gee, 0 or 0? Well, I'll look it up. It's a 0. Just notice there that he first of all asks, there's 3 different circuits. What would be the output when the upper one is 1 and the lower one is 0? And then he wants you to go through those same 3 circuits again with the opposite. The upper input is 0 and the lower input a 1. You may have, yeah, I mean, if we did it there, the answer would be a 1, right? We'd have a 0 going into the NOT. That would be a 1. The 1. So 1 or 1 is 1. You don't have to draw the circuit itself. If you're concerned and want to explain what's happening, that's fine. But all I really need to see there is what would the answer be. There'll be 6 parts to this, right? There are 3 circuits, A, B, and C, and there's 2 cases, when the upper input is a 1 and lower is 0, and then vice versa. Just be sure to label it so I know. Brookshire's labeled the circuits A, B, C, and then just tell me, you know, for upper input 1 or lower input 0, and then the vice versa, just so I can tell what's what there. Okay. All right. Question 24. Write the number 23 in 2 ways. Really? Write the number 23 by representing the 2 and 3 in ASCII, and then write the number 23 in binary. And by binary, he really means base 2 binary form. Brookshire gets a little sloppy. He's oftentimes saying binary, and I told you that doesn't mean anything. That's just 1s and 0s. He'll oftentimes say binary when he means base 2 binary form. Now, you need to think about this. If you can understand that one, then you really see that concept of data and metadata and the description of things. Write 2-3 in ASCII, write 2-3 in base 2. 26 asks you, A through F only means you only, don't do just A and F, do A, B, C, D, E, F, do those 6. But there are more in there. And they're just numbers that I want you to convert from base 2 into base 10. And then there's another one. This is not a question in the Brookshire text, but I want you to answer it. Create an algorithm for the JPEG compression standard. You'll read about the JPEG compression standard in section 1.8. And then I want you to create an algorithm for it. Just remember what we said about algorithms. Detailed, unambiguous, they state how. 4 basic things here. Questions 1, 24, and 26 in Brookshire, and then mine. So 4 things you'll do for there. I didn't mention this before. I want you to put all these into one document. Please don't upload 4 different documents, one with each thing. Just put everything together in a single document that you upload. And again, if something goes wrong and you discover after you've uploaded a document that something was missing or wrong, you can re-upload again. You cannot, however, recall or delete your own upload, but you can upload one again. If you do that, just identify this in the title as revised or updated or something. Typically, unless I know otherwise, if you have 2 things submitted, I'll delete the earliest one and only look at the later one. 2b. Chapter 2 in Brookshire. So again, these are in the 11th edition. These are problems beginning on page 102 in the text. Question 8. Suppose a machine language is designed with an opcode field of 4 bits. You're going to have to read what in the world an opcode field is. How many different instruction types can the language contain? So in other words, the opcode, which specifies instructions, is composed of 4 bits. How many different instructions could it have? And then the second part of that question, what if the field was increased to 6 bits? 45. How many bits per second must a got to read it. How many bits per second must a keyboard transmit to keep up with the typist typing 40 words per minute? Well, I'm looking for a value here. But here in this one, I want you to show your work. And I should mention this. This applies to everything except for that very first one with the gates. It's a little hard unless you're going to include the picture and show things just like I did there to show your work. So a value's okay. But here's what I mean by show your work. In 45, if you just listed a value, I'd say fine, but that's not enough. How did you arrive at that value? 52. Identify 2 approaches to increasing throughput. This relates to the processor and kind of relates to that speed thing I wanted you to think about. But read about it. And here, again, when it says identify, don't just list 2 words. Explain those and how that does really increase throughput. 2C, chapter 5. First one asks about creating primitives for an algorithm for a subject that you are familiar with. So we talked about algorithms and primitives. Note that I really want you to focus on the primitives. That's what I was talking about with snow plowing, what backdrag might be, etc. So apply it to your own special thing. In what sense do the following steps not constitute an algorithm? You should probably read these rather than trying to memorize what they are. So Brookshire number 6 is going to give you some things that look like instructions and may actually be instructions, but are not really an algorithm. So there's 3 steps there. Tell me why that isn't an algorithm. You figured out that how to shoot a trap was not an algorithm, right? 18. 4 prospectors with only 1 lantern must walk through a mine shaft. At most, 2 prospectors can travel together, and any prospector in the shaft must be with the lantern. When you read that, your question is going to be, what does this have to do with information technology? And the answer is, this is about problem solving. This is your classic word problem. I want you to see, again, Brookshire talks about this a little bit in the text. This is a classic word problem that if you think about problem solving, it will help you get to it. Some of you may have seen this before, so it's not exactly frightening. But if you haven't seen it before, it's going to seem weird. And I'll just warn you, the first time you solve it in what you think is a straightforward way, you'll discover that you haven't solved it fast enough. Okay, show your work for all these things. The final one, there is nothing to turn in, but I want you to be thinking about VB script because I'm going to ask you to investigate that after day 4, and ultimately VB script is nearly the foundation of what macros use, and that's Visual Basic for applications. So just a way to kind of slide into seeing some things. So you saw that tutorials point before the old compile online. So just, okay, I won't know if you did this or not, but if you could get this going, that will really help you for the next week when you have to read the chapter and do the quiz on it, and it'll certainly help you when you have to do the macro on it in the next unit. So nothing to turn in for this one. Now again, if you want to get ahead, you can look at D, E, F, and G. G is a quiz in the coding text. It's on the chapter on VB script, chapter 13. I'd recommend that you actually work with VB script a little bit here before you do that. But as with the other quizzes you've seen, it's timed. So don't begin the quiz until you're ready. Don't just start this and hope you can find the material in the book fast enough. That's not what I want you to do. Be familiar with it and then do it. Are there any questions about any of these assignments? Upcoming ones, perhaps. Yes, that's correct. Don't forget that there are still, is it only 2? There are still some other ones potentially. One of those is not due for a while. That's the one on critiquing Angel. You already did it. It's not a problem. But if you decide you turned it in already and want to update that later. So the one on critiquing Angel is still a couple weeks out. And then we had another one. What was it again? Okay, what is IT? Thank you. That also you have a little more time to think about. Yeah. Okay. A lot to keep track of. That's why I recommend you look here too. So this will tell you, right? Even though I only assigned you 3 things today, notice there are 4 things due. That's because, again, there is one of the, here's 1H. I guess that's what is IT. Right? And even though there's 4 things assigned here, you notice 5 due here, and that's because one of these is critique Angel. Exactly. Okay. Now you'll notice that none of the ones in Unit 2 flow out of the unit. Same thing will happen in 3. By the time we get to Unit 4, there's the lowest number and likely the easiest to deal with. Okay? We are done on March 19th. That's our 8th class meeting. We will meet that night. We will talk about some material. And also that night we will take the exam. There's only a single exam in this class. It does cover potentially any topic that we've discussed in this class. On the one hand, that's frightening. On the other hand, it is 50 points, which although is larger than any one assignment, compared to 350 points of assignments, it's not overpowering. Slipping up, doing well up until that point and slipping up on the exam has hardly ever cost anybody, a letter grade or anything like that. And the flip side of that, I've seen this happen where somebody comes in kind of not even borderline but below that and just really do extremely well in this final and move themselves up. So don't panic. Sometimes, all the time, tests are stressful for sure. But this will likely, even if you do poorly, it won't horribly affect your grade. Flip side is if you do well, it could have every possibility of increasing that grade too. Any other questions or comments? Okay. Distance folks, weeks, I think we're nearly done. We're going to do some lab-based material, and you've got some other things similar to do to that. But I think that's the last you'll hear me on the course cast for this evening.